If you've ever taken a chemistry class, you've definitely run into the mole. It sounds kind of weird, maybe a little intimidating, right? But what if I told you it's really just a way of counting? In this explainer, we're going to break down one of chemistry's most important ideas and show you exactly how it lets us count the uncountable.
So here's our game plan. First, we'll dig into a big problem that chemists face. Think of it like a recipe gone totally wrong. Then we'll introduce the brilliant solution they came up with and try to get our heads around just how huge this idea really is. And finally, we'll see how it all works in the real world, using something as simple as a penny and, yeah, a can of soda.
All right, let's jump right in. At its heart, chemistry is all about things combining to make other things. But here's the real question. How do you make sure you have the right amount of all your ingredients?
You know, a chemical equation is basically just a recipe. Seriously, think about baking a cake. The recipe tells you need 2 eggs, 1 cup of flour, and so on. While a chemical equation does the same thing for a chemist. It says, hey, you need exactly 2 atoms of hydrogen and 1 atom of oxygen to make 1 molecule of water. It's all about getting the count of your ingredients just right.
And this is where it gets tricky. I mean, you can't just reach into a jar and pick out 2 hydrogen atoms. They are impossibly, invisibly small. All you can do in a lab is weigh stuff. But if you weigh out 1 gram of hydrogen and 1 gram of oxygen, you have totally different numbers of atoms. So how on earth do chemists actually follow their recipes?
Well, they came up with this really clever solution. They invented a special counting unit. You know how we have a word for 12 things? A dozen? Chemists needed a word for a specific, and I mean very large number of things.
And yeah, this slide really puts the scale into perspective. A dozen, we all get that, it's 12. A mole, which is kind of like the chemist's dozen, is, well, just a teeny bit bigger. It's 602.2 sextillion things. Honestly, it's a number so mind-bogglingly huge that it's pretty much meaningless without some context. And don't worry, we are definitely going to get into that.
So here it is, the formal definition. The mole is just a unit. It's a word that stands for a number. And its whole job, right? It's to be a bridge. It connects that microscopic world of atoms we can't see or count to the macroscopic world of grams that we can actually measure out in a lab.
And this monster of a number? It has a name, Avogadro's number. We usually write it in scientific notation, 6.022 times 10 to the 23rd, mostly so you don't have to write out all 21 of those zeros. That's the magic number of particles in 1 mole of anything.
Okay, but how big is that number, really? It's one thing to see it written down, but it's another to actually grasp it. So to really get a feel for this, let's try a little thought experiment. Let's imagine we're trying to get a mole of something we can actually hold.
Let's say we're heading to the store with a very specific shopping list. 1 mole of toothpicks. I mean, a mole is just a number, so it should be possible, right? Well, let's run the numbers and find out.
Okay, so the plan is pretty simple. We'd start by figuring out how many boxes of toothpicks we need to get to that giant number. Then, how many shipping cases that would be. From there, we can get the total cost, and then, just for kicks, we'll figure out how long it would take someone making a pretty good salary to pay for it all.
And the final bill for our toothpicks comes to $422 quintillion. Let me be clear, that is more money than exists on the entire planet, by a lot. The entire world's economy is literally a rounding error on our toothpick bill.
Okay, but what if we could get a loan? How long to pay it off? Well, it would take you, wait for it, over 7 quadrillion years. Just to put that into perspective, the entire universe is only about 13.8 billion years old. You wouldn't even make a dent.
And that's the whole point, right? The mole is an absolutely, ridiculously, uselessly large number for counting everyday objects. The whole reason we did this toothpick exercise was to show you that this number was specifically picked because it only works on the tiny, tiny scale of atoms.
So, now that we've established the mole is completely absurd for toothpicks, let's see where it becomes this total game changer. We're going to take a super common object, a penny, and use the mole to do something that sounds impossible. Count the atoms inside it.
Now, to do this, a chemist just needs a couple pieces of info. We'll use an older penny from before 1982, because we know it's about 95% pure copper. Then we look at the periodic table for something called the molar mass of copper. And this number is the magic key. It tells us that if you have 63.55 grams of copper, you have exactly 1 mole of copper atoms.
And the process from here is so beautifully simple. First, you just weigh the penny to see how much copper is actually in there. Then, using that magic molar mass number, you convert the weight in grams into a count of moles. And once you know the moles, you just multiply by Avogadro's number, and boom, you have the number of atoms.
And this is the mole's superpower. Using this simple idea, we can say, with confidence, that a single penny holds about 28 sextillion copper atoms. Think about that. We just used a scale in a lab to count a number of things far greater than all the grains of sand on every beach on Earth. It's incredible.
Okay, so this whole bridge idea between weight and numbers, it's not just for simple stuff like copper atoms, it works for big, complex molecules too. Let's take a quick look at one more everyday item, a can of soda.
Your average can of soda has about 39 grams of sugar in it, which is mostly a molecule called sucrose. Now, by just adding up the molar masses of all the individual carbon, hydrogen, and oxygen atoms in its formula, we can figure out that 1 mole of sucrose weighs about 342 grams.
And look, the steps are exactly the same. See how powerful this is? We take the mass we can easily measure, the 39 grams of sugar, and we use its molar mass to translate that into moles. Then, one more step with Avogadro's number gives us the final count of every single sugar molecule in that can.
You know, this quote just nails it. The mole is the essential tool that makes all of modern chemistry possible. It lets chemists follow their recipes perfectly by bridging that gap between the world we can see and touch and the fundamental atomic reality that makes it all work. So, I'll leave you with this final thought, to really put it all in perspective. 1 mole of water molecules is about 18 milliliters. That's a tiny little vial you could easily hold in your hand. Now, thinking back to our toothpick adventure, do you think you could even fit a mole of M&Ms inside your kitchen? Or your house? Hey, thanks for diving into this with me. Hopefully the mole feels a little less mysterious now, and a lot more like the incredibly clever and essential tool that it is.